Okay, good morning and welcome back to the lectures on Hamilton-Jacobi equation. This is the third lecture in the section Hamilton-Jacobi equation. So let me briefly recall what we have done in the previous class. We have basically derived the equation, the Hoflag's formula for a minimization problem. Since we need to do some computations, I have a kind of a typed material here because doing the computations will take a lot of time. So what we have done in the last class, we have introduced the minimization problem, and the uxt is the minimal value of this functional integral 0 to t l w dot of s ds. W varies overall, so w varies in at we have defined all the C2 trajectories taking values from 0 and x. Okay, at t equal to 0 it's y, and at t equal to time t it is x. So you are minimizing. And what we have done, two important assumptions we have made. One is about the Lagrangian. L is called the Lagrangian. You will see more types of Lagrangian here. And we have seen two conditions. One is the mapping L is a continuous and convex function. Convexity is an important assumption. Of course, one can consider non-convex problems, etc. So for this particular thing, where you are derived Hoflag's formula, we have used this one. The second part is a coercivity condition, and that means L has a superlinear growth. Something like a growth like this. Need not be in this form, but you need a growth which is bigger than your mod q. Okay, and then we have derived a Hoflag's formula that if L is satisfies the above condition and G is continuous, then U satisfies this minimization problem. The difference between this minimization problem, this minimization over trajectories, okay, on the other hand, this minimization over Ra. So that's the difference. So we are going to use this Hoflag's formula to derive some properties of this thing. Eventually want to show that U satisfies some Hamilton-Jacobi equations. What we are using is that we have started with a minimization problem and converted that minimization over trajectories into a minimization over what we call it an Euclidean minimization. That's a kind of finite dimensional minimization. The over trajectories is an infinite dimensional minimization. So we are going to use this formula in deriving some important properties of U, and that's what we are going to do in this lecture. Okay, so we are going to derive what is called a functional identity. Okay, this functional identity, that means U is the solution given by the Hoflag's formula. As you see here, it's a formula given by this formula, which is the solution to that one. The advantage of this is that because you are taking an infimum over R, and then you know that compute its derivative, and you will be able to get explicit formula for your solution. Okay, so what we are going to do, we want to understand certain properties. Showing that it satisfies certain Hamilton-Jacobi equation, first we need to introduce what's a Hamiltonian, which we will not do it today, and maybe a next lecture or a lecture after that. Okay, so what we have seen is that there is a functional identity relation. This is a very, very important formula. Uxt is equal to, so look at it. So you want to compute, so you basically want to compute U at time t. So you take any time s less than or equal to t. You can take any s and then compute your minimum value at s, t equal to s, with uys. And y can also, so you fix a y in Rn and then you compute uys. So accordingly you will have a formula here. So this is xt. This formula is valid for all x and t. So you compute uys So what you are doing is that you compute, so that's what you compute UIS for any s less than t, and then use u dot of s as your initial value over the interval s to t. So you are looking at it, you have the initial value here y. So you're starting with an initial value at t equal to 0, and then you have computed this computed this. But on the other hand, you compute the minimum value required and at s time s, and then take this as your initial condition and in the interval s to t, and then compute u dot to t by a minimization. So for that, so you understand the cost from on that interval is precisely if you can connect these two in the any dynamical system. If you want initial value and if you want to compute something at some other point, you can take any other initial value and then compute from here. Okay, and then you have this portion, and that's what he exactly tells you. This is an important thing of a functional identity, because it's an identity between you about the functions at the functional level. Okay, and this is very good. This is also called what is called the dynamic programming principle in optimal control and optimization theory. So this is basically the and actually an infinitesimal version of this. So this is a functional identity, an infinitesimal function of functional identity, namely dynamic programming principle, will lead to Hamilton-Jacobi equations when the solution is smooth. When the solution is not smooth, how do you interpret that way? That's the thing. So let me try. The proof is bit of a technical thing, but basically cleverly using the Euler-Lagrange formula. So you see, I have to prove this equality. So I call this equality to be star. Okay. So you want to prove that equality star. So I look at it UIS. So I take UIS. UIS also you can apply Euler-Lagrange formula. So this is given by a minimum. UIS is given by a minimum. That is this y star. So because UIS is a minimum, you can write here UIS. You use another parameter when you write YS here. And then the infimum is achieved when you have L is a quadratic growth and all that. You can see that that's where you use the assumptions. You can see that a minimum is achieved at some point y star, and which we are going to use it repeatedly. So you will be able to choose y star in Rn where the minimum is achieved. So your minimum is achieved. Minimum is achieved for UIS. So you write down the Euler-Lagrange formula for UIS, use the parameter properly, and at y star. So the minimum is achieved at y star. So that's why you get UIS is equal to GY star. So you are using the precise information where the minimum is attained. Okay. So hence you apply again the Euler-Lagrange formula for UXT. UXT is again is a minimum. You see. Hence since it is an infimum, this is true for any y. UXT will be less than or equal to this bracketed quantity for any y. In particular, UXT will be less than or equal to y star at that point. So you are here, you are only using the inequality, but in the minimal thing here you have an equality. So you have used this equality by attain the minimum. Here this result will be true for any y, in particular for y star. So you have again applying the Euler-Lagrange formula here. Now you have a trick. This is the trick you are used. So now you want to represent, this is the term you want to get it. So you see, this is the term you want to get it. X minus y by t minus x. So I am going to write L is a convex function. Now I am going to apply the property of convex functions. So you write your x minus y star by, and this term you want to come inside. And that's what you are going, you want to prove the one-way inequality first to prove that one. So you have to get this term on the, so you have to get this term on the right hand side. So I want this term to come to into picture. So I will do that. So I will write my x minus y star by t. You can verify this, verify. So you can verify. Okay, so you verify that I'm writing x minus y star by t is equal to 1 minus st into x minus y by t minus s. That's easy to check, because if you take t in here, t minus s by t minus s and t cancel, the s cancel, you will see it's exactly x minus y then. Now you see this is a convex combination, means 1 minus s by t plus s by t is 1. These numbers are less than 1. S by t is less than 1 because s less than or equal to t. This is also less than or equal to 1. So it's a convex combination, not just a linear combination. This is a convex combination. Okay. So you have your convex combination. So I can apply convexity. Apply convexity, what you will get it? You will get L of x minus y star by t is less than or equal to 1 minus s by t into L of this one plus s by t, L of that. So you can apply convexity and use this one, and you will have a term and then use this term together. So I have left some computations here. Do the computations, okay? That's an exercise. Do the computation. Some computations I have left, which you have to learn it. It's simple, because I apply L of x minus y star by t is less than or equal to 1 minus s by t into L of x minus y by t, and that is this term, and then s by t into L of that. But s by t and 1t will cancel in your uxt formula. This t will get cancelled and you get exactly this one, and that's your uist. So you take the minimum over that. So you get this equality now. Do the computations and you get, this is just one line computation applying L on this one, and use these two formulas which we described above, and then you get this one. So you have this formula, and then this is true for any y, and you have one-way inequality. You see. So you got one-way inequality. Now you have to get the reverse inequality. So you have to get, to get the other way inequality, you use the trick which we have used. What is the trick we have used? Two steps we have used here. One, we have exactly computed equality where the minimum is achieved for uys. And then just the infimum definition is used for uxt. To get the other way inequality, you use the minimum for uxt. Okay, so that's what you are doing it. So you apply the Hoflag's formula by minimum achieved. So minimum achieved. So here you are using it for achieved for uxt at x star. So that's what you apply. So you have your equality correctly. Again, it's a similar trick. I want to get other terms. I use my y little more cleverly here. I will write y as a convex combination in this form. I write choose your y as a convex combination of them. Once you use it, you can get this equality formula. Okay, compute it. Can see that all these three are equal. And this is what you want to compute it, because this has to come to the left hand side. So you see, if you look at here, this is right hand side. So you have to come to the left hand side. So you come back to the left hand side and you have your L of x minus y by t minus s. Look at here. And I can write here, and then x minus y by t is equal to, I can apply this here, t minus s into L of x minus y by t is same as, so I replace correctly. So there is an equality here. So this there is no, I'm not applying the convexity property here. X minus y by t is same as x minus x star by t, and you write your uis now. your UYS is already there. UYS is less than or equal to this one. So for UYS, this quantity, this again by infimum, this quantity is less than or equal to this quantity. You see, this quantity is less than, because you apply the minimum at X star. So exactly earlier, so that basically you are reversing the role of UYS and UXT and writing down the properly. So once you do that one, you will have y minus x star by s is same as x minus x star by t. So s and this cancel, you get t into L of x minus x star by t and your gxt, and that's nothing but your uxt here. Okay, so you get so you have this formula less than or equal to this one uxt. Now you take infimum over all y. That's what you want to show it. So you want this to be on the side. This is true for any y. So you take infimum over y in here. So okay, infimum over y, infimum in this case. Okay, so infimum here. That's the question. Infimum here you will get is also less than or equal to uxt, and this completes the proof of your important functional identity which you are getting it. Please understand it physically. Okay, for any s you look at its minimal value and start that. So you are have a trajectory basically. So look at the minimal value at time t equal to s basically, and take that as your initial value and proceed your compute your cost basically, and take over all such possibilities of y, and then you will get back your uxt. Some sort of a comparison between what you see it in the ODE. Yes, okay. Yeah, that's what I remark. Compare this with a semi-group property enjoyed by a ODE system. This property is part of any abstract dynamical system. So you proved the Hoflax formula. The minimal value given by the Hoflax formula satisfies a dynamic programming property. So we are now going to derive. So this is one thing. So you have your theorem 2 basically. That is about the Lipschitz continuity. That's what we are looking for it. Lipschitz continuity. Okay, and then not differentiability. So the solution given by u eventually happen to be the solution, need not be differentiable, but it will be more than continuity. In fact, it is uniformly continuous in the variable x. So you are assuming S is G is Lipschitz continuity with the Lipschitz constant K. I hope all of you know what the meaning of Lipschitz continuity. Okay, then otherwise you look into our earlier lectures or any books you can refer to for that matter. Lipschitz continuity, assume G is continuous with the Lipschitz constant K, then the function u dot of t given by the formula is Lipschitz continuous in R with constant K, and that K is independent of t. You see, so ux1 minus ux2 t is less than or equal to k. This is true for all x1 and x2. And further, you also satisfies this. We have not described any PDE problem, but it satisfies an initial condition, and this is going to be part of your PDE later when you introduce your Hamilton-Jacobi equations. So you see, so there are two steps. So the Lipschitz continuity proof is not difficult, but this proof of this initial condition deriving that ux0 is equal to g of x involves little extra work, okay, which we will do it. So to prove this again is not difficult. So you look at this is what you want to compute. You have to compute ux2 t minus ux1 t because you want to consider the modulus. So you have to compute ux2 t minus ux1 t. And the other way also ux1 t minus ux2 t. So you see, now look at here. ux2 is given by this Hoflax formula. Okay, Hoflax. So I'm just writing infimum. But you can write infimum here, but I will not be, because of the minus sign. Infimum cannot be estimated. Infimum of something is less than or equal to for any element, but minus of infimum only it will reverse this thing. But here for ux1t, I compute the minimal value it achieved. So the corresponding to x1, there will be an x1 star t for which ux1 t is achieved. So x1 star t, yeah, it is already mentioned here, so I don't have to mention. So x1 star is the minimizing point in the Hoflachs formula. So this is exactly equal. It's not that I am removing the infimum. I am looking for it. And for this point, now I will cleverly choose my y. I want this. I don't want my L here. So to L here, I choose my y like this. If I choose my y here, I will get exactly x2 will get cancelled here. I will get x1 minus x1 star. So t and this term will get cancelled. So I will get this will be less than or equal to. So this is infimum. This is true for any y. Because now I can use, because this is a positive side. So I can choose for infimum anything. Because of this minus in the second term, I have a problem. So I choose y equal to x2 minus x1 star minus gx1. And g is Lipschitz continuous. So there will be less than or equal to k into this minus this. And x1 star and x1 star cancel. So you get. So ux2 minus ux1 and get it. Now reverse the role of x1 and x2. And we reverse the role of means you compute ux1t minus ux2t, and in this case you choose ux1, you write it as an infimum, and for ux2 you choose the achieving point, that you look for an x2 star so that ux2t is exactly achieved at that point. So that gives you your Lipschitz continuity. And I want to check my initial condition. So I'll go to the initial condition. What is the meaning of initial condition? I want to ux0 is interpreted as a limit. Limit t tends to 0 uxt. Okay, I want to prove this is equal to g of x. This is what I want to prove it. Claim. This is the claim I want it. Okay. So you use the Lipschitz property. So it's not difficult, but it is a bit of a technical thing. So you look at here. So this term is this one. So I use this one. And this one you apply Lipschitz continuity. By Lipschitz, gy minus gx. I know that modulus of gy minus gx is less than or equal to k into mod x minus y. But then if I want a lower inequality, you put a sign. This is true. Mod x minus y greater than or equal to minus k of mod x minus y. That's true. You see. So gy minus gx, and that's what I kept it here. So gy put it here, gx and minus k I have taken here. So this is just an application of the Lipschitz continuity of that one. So that is gx. So I take t and put z equal to x minus y by t. Okay. So that's a notation given here. Now you have to understand. I want to minimize this with respect to y. But x and t are fixed. So the minimizing LHS is equivalent to minimizing z, because x and t are not changing. So when you want to minimize something, whether it is if you are not convinced, just verify that. So the minimum over this is same as minimum over z. So it's enough to minimize over z. So once you do a minimizing over z, so minimizing over z or y doesn't matter, equal to minimizing. So if I minimize here with respect to y, I get my gx, and if I write the minimization, I get this term. So this is greater than or equal to uxt greater than or equal to gx into, so I am minimizing, whether you minimize over y or minimize over z is same, because x and t are fixed now. I am not varying that. So minimizing this, you get it, this one, and this is gx less than or equal to, when I want to take this minus outside. So when I take a minus outside, so there is a big bracket here, careful here. When I take minus outside, it will become a supremum. This is wrong. There is nothing here. There is nothing. Now here is some more trick which you want to understand. You have to understand the coercivity of L. What does the coercivity L tell you? So this is linear. So you see the linear. And this will quadratic. Quadratic. So as mod Z is large, this will go to basically minus infinity. So you have to understand that little bit of an analysis here. Okay. So this is a guy going to, because of this quadratic growth, this is go to infinity. So minus that will be going to actually minus infinity as mod Z tends to infinity. What is the implication of that? The supremum cannot be achieved when mod Z is larger. So that means that supremum is achieved. This implication is that supremum is achieved in a ball of radius r. This implies that this one achieved in B R0 for some r positive. So if you are trying to look for the supremum may be in a ball of radius r. And this r is fixed now. So what I am saying is that this supremum over Rn is less than or equal to supremum, because after r it will be very, very small. So the supremum, and I call this, now the supremum is on a closed set. So the supremum is achieved. I call this to be C1. Therefore, you will see there is a minus sign here. The supremum of this one is less than or equal to a positive constant. So therefore uxt minus gx will be greater than or equal to minus C1t, because it is supremum is less than or equal to, since the minus sign is there, so you get this inequality. Okay. And of course uxt is always, this is true for any number. This is from the infimum. In particular, when x equal to y, you get L0, because t into infimum of t into L of x minus y by t. Once you choose y, you get L0 here by choosing y equal to 0. That means you get, this implies you get uxt minus gx will be less than or equal to t into L0, which is another number, t into L0. So you have uxt minus gx greater than or equal to minus t, and then uxt minus gx is less than or equal to t into L0. So if I choose my t is equal to this one, and you see that your modulus is this one, because uxt minus gx lies between these two numbers. Okay, minus C1t and my t L0, which is another number. So if you choose C, you get one. This proves that as t tends to 0, uxt, so this implies uxt tends to gx as t tends to 0. So you see, so basically what we have, so before concluding this part and continuing little more, and we will introduce something more general. So you have, we proved the functional identity, we proved Lipschitz continuity, and we proved uxt. So the next we actually want to see that what is the HJB, Hamilton-Jacobi equation, satisfied by u. By u. For that, what is H? First of all, what is H? So what is this Hamiltonian? This is called Hamiltonian. We will come back to this later, maybe in the not another couple of I will do something more here today. So, and more examples of this kind of minimization problem before coming to H. And H is called basically the Hamiltonian, and you eventually prove that this is what you will prove. You will prove ut plus h of du equal to 0. And this we will draw it after next lecture or a couple of lectures later. Okay, because we need to introduce first of all what is H. So before completing today, what I'm going to, I wanted to actually complete one more section, but that's not possible. I'm going to study little more general. So what I'm going to do is the more general. We have studied one calculation problem, so we are going to study more general CV and Euler-Lagrange equations. Euler-Lagrange equation. So I will do the setup today, Lagrange equation. And then we will give some examples, and after that we will come back to Hamilton-Jacobi equation later. Okay, so we are going to consider a little more general calculus of variation problem. So let me have my notations first here. So let me set up the notation today, and then probably we will do tomorrow the other thing. So notation is, we are going to consider variable LXQ. That means L is a mapping. I will use this as a Rn, X is in Rn to Rn. So to see that in these are all more general than the classical mechanics and Newton's law of motion, which you will see here. Okay, so in the terminology, X is always is the position, which you will see. Need not be in general. In mechanics, it's going to be like that. We'll give the example precisely, and more general position, and this always represent the velocity. So eventually Q is going to be something like X prime. Okay, later. But right now it is at least a general function which will have an applications, and you recall AT. Already defined the set of all admissible class AT, which you will do. Set of all twice continuously differentiable functions satisfying at t equal to 0 y, and at t it is x. So set of all trajectories here. So I will also put a notation when I have this is an n vector. So I will have my dx of L is all the derivative with respect to x of L. Okay, and the derivative with respect to Lx2. So this is a vector Lx, and similarly I will have dq of L is the next n vectors q1 etc. Lqn. Okay, so you have these notations to be used. We continuously use these notations, and L is called Lagrangian. In the earlier problem which we have described is more special than this, in which the dependence of x was not there. There were only dependence of q. So what is your minimization problem? So you have your minimization Jw is equal to integral 0 to t L of W of S W prime of S. I told you this is something like velocity into ds. So in this generality, I don't write the g function. You can include that cost also, terminal cost, initial cost or terminal cost. But let me concentrate only on this part, and that's what more important. The other part you can add, and there is nothing wrong in adding that one. Okay. So as you know, probably we want to derive the aim is to derive Euler-Lagrange equations. Euler-Lagrange equation. So what is the problem? So the problem is find W bar such that J of W bar is equal to minimum of J of W over 8. So we are going to do that minimum thing. So these Euler-Lagrange equations are necessary conditions for optimality. Necessary conditions for optimality. So let me recall. Suppose you have a one-dimensional situation, n equal to 1. I want to find f of x naught. Say minimum of f of x in some set, an interval or something like that. Then you that if x naught exists, and f is differentiable, that implies f prime of x naught is equal to 0. So you see, so this is a necessary condition. It's not a sufficient condition, you know that. Necessary condition. Now what we are doing is that we are doing a minimization problem, not on finite dimensional domains. We are doing a minimization problem in an infinite dimensional setup. And then what do you mean by, yes, we already got a W bar, but then you have to understand the differentiability of J. And there are concepts of modern concepts like differentiability, what are called Fresher derivatives and total derivative in infinite dimensional setup. And we are going to derive a necessary condition if W bar is optimal, which minimizes thing. We are going to derive what we call it the Euler-Lagrange equations, which is going to be a system of second order ODEs. So we will stop here and continue in the next class, and then we will give some set of examples. Thank you.